Good morning to all of you. So for today's lecture, we're going to concentrate on the topics of electrostatic, which is the second part of EMT. So the first part of EMT is on electrostatic. So we have successfully covered it from week 1 to week 7, yeah, and also last class on Tuesday. Okay, so from today's onward, the topics will be on the microstatic, yeah, electrostatic field, and these are the excerpt from the CI, cost information. We're going to see about the application of Biot Savart law, yeah, Biot Savart law to determine the magnetic field intensity for arbitrary current distributions, including filamentary, surface, and volume currents, yeah. So which means that we're going to see how we can calculate the magnetic field intensity by using the Biot Savart law produced by this particular source of field, which include the filamentary, surface, and volume currents. Yeah. Okay, so this will be the topics to be learned for lecture 15. We're going to understand the magnetic field intensity and what are the sources that can generate the field, and subsequently we're going to learn about the Biot Savart law. The reference for this lecture 15 can be obtained from Sadiku page 291 to 301. So these are three objectives for this lecture 15. Number one, you must be able to understand the concept of electrostatic intensity, yeah, and you must be able to differentiate between the electrostatic and electrostatic field intensity. Yeah. Number two, you must be able to understand what are the sources that can generate the magnetic field intensity. And number three, going to use the first law, which is the Biot Savart law, to calculate the magnetic field intensity based on the sources that has been learned in part 2 or in the second objective. Okay, so these are three objectives that we're going to learn in lecture 15. Okay, so this is the introduction, short explanation about the magnetostatic field, or in short, I just call this as a magnetic field. Yeah, so it's understood that when I say magnetic field, it's understood to be a magnetostatic field intensity also. Okay, so the word magnetostatic comes from two different words, which are the magneto, which stand for the magnetic field intensity, and the static, which stand for the source itself. Okay, so the symbol for the magnetic field intensity is a vector of H. Okay, and the unit for it is ampere per meter. Okay, and the sources of this particular magnetic field is a steady current, or we just call this as a direct current, DC current. Yeah, it's a DC current. Okay, that's why we call this as a static, because we have learned previously in chapter 5 that the charge which is moving can be is known to be a current. Yeah, I is equal to dq over dt. So in this particular case, the charge is moving, but the movement of the charge is in constant velocity. Yeah, constant velocity. So there should be no acceleration, and due to the constant velocity, the current is said to be a steady current or a direct current. Yeah, and the case whereby the charge is accelerated, we're going to have a current which is considered to be a time varying current. Yeah, so that should be the source of time varying field that will be learned in the third part of EMT later on. Yeah, but for the time being, we assume or we understand that the magnetic field intensity is due to a steady current, which is produced by the charge which is moving at a constant velocity. Yeah. Okay, so there are three types of sources which can be used to generate the magnetic field intensity in general. We can have the filament current, we can have a surface current, and we can have a volume current. Okay, I would like to relate these ideas of field sources with the field sources of electrostatic field, which has been learned in chapter 2 before, if you can remember. There are four sources that can be used to generate the E field. We have the point charge, we have the line charge, we have a surface charge, and we have a volume charge. Yeah, this is a charge in terms of line, charge in terms of surface, and charge in terms of a volume. Okay, so the same things applied for the case of source of magnetic field intensity, where we can have it in terms of the filament. Yeah, filament is somehow like a line, yeah, a line current. We also call this as a line current. Yeah, I can just call this as a line current. It's understood to be a filament current. We can have a surface current also, and we can have a volume current. Yeah. So most of the time, I will try to relate what we have learned previously in electrostatic with the current topics of electrostatic, because both field intensities are almost similar in terms of its explanation. Yeah? Okay then, so let us proceed with the sources one by one. We go for the filament or line current first. So as the name implies, the current is in terms of line, and we can represent the filament current to be having a symbol of I. Yeah, I stand for the symbol for the filament current or line current, and the units for this I is A, ampere. Okay, and knowing that the current do have a direction, yeah, the flowing is in certain direction, so we must then represent the current to be in terms of its current element. And for the case of the filament current, we take one segment or one short element in the filament itself, and we label this as a vector of dl. Yeah, it's a vector of dl. Yeah, and this filament current element, yeah, we call this as a current element. And for the filament current, the element is I dl vector. Yeah, I dl vector. So from this, we know that the units for the current element will be ampere meter. Okay, for the case of electrical intensity last time, remember that the source is in terms of dq for the line charge, for instance, yeah, and we have a rho L dl. Remember, yeah, a dq, which is the current element, sorry, charge element, and for the case of line charge, it is rho L dl. So this is the charge element for the line charge case. So the same things applied here for the case of filament current. The current element is I dl vector. Yeah, so you can see somehow the pattern is there. Yeah, the pattern is there. The difference is that we have a static charge of rho L, and here we have a moving charge, which is in terms of current I. Okay. And then we have the second types of current, which is a surface current density. Yeah, surface current density. And for the surface current density, we label it as a JS vector. Yeah, a JS vector, right? And it has its own direction, JS vector. The unit for the JS vector is ampere meter, yeah, ampere per meter. Yeah, we call JS vector is a surface current density. And for the current element, if we consider a small area on the surface current, the area is having a magnitude of ds, area of ds. So the current element for the surface current is Gs vector ds, and the unit still ampere meter. So we compare this with the surface current charge, or sorry, the surface charge density last time in electrostatic. You know that for the surface charge, the dq is given by rho s ds. Yeah? So this is the current charge element for the case of a surface charge. So the same thing is applied here for the case of surface current. We have the current element to be equals to the Js vector ds. Yeah? So please be noted that the current element is in terms of vector. Yeah? It's in terms of vector. For the case of filament, is IDL vector. For the case of surface current, it is Js vector ds. Yeah? Okay, so the third general representation of the source that can be used to generate the magnetic field will be the volume current. Yeah, the volume current. And for the volume current, we represent the volume current is in terms of J vector. Yeah, that should be the symbol of the volume current density, J. Yeah, J vector, and the unit is ampere per meter squared. So I believe that we have seen this J vector last time in our lecture on chapter 5. Yeah, J vector when we learned about the current. Yeah, about the current. So I believe that you have seen this J vector basically related to the conduction current J. Yeah, J equals to sigma of E. Okay, remember last time, yeah, in chapter 5, yeah, we have learned this conduction current. Okay, so this is very general representation for the current. Yeah, the one that we have here is a very specific. The one is very specific. This is the conduction current density, which is the current that is flowing in the conductor. Yeah, but what we have here is quite general, which is just a J vector. Yeah, volume current density. The units is ampere per meter squared. Yeah, and if we consider an element of the volume, inside this volume current. Let's say the element is a dV, so we can have the current element for the volume current to be J vector dV, still in the units of ampere meter. Yeah. So these are three main sources in general that can generate the magnetic field intensity. We have the line current, we have the surface current, and we have the volume current and its respective current element. If we can write here, we have I dl vector for the line current, we have J S vector ds for the surface current, and we have J vector dV for the volume current. So these three are the current element. Okay, so now we have understood that these are the sources that can generate the magnetic field intensity, but how, how can we calculate the magnetic field intensity with these given current element or the field sources? Okay, so that will be our next objective. Yeah, so before that, let us recall the things that we have learned previously in electrostatic. We have learned that in Coulomb's law, chapter 2, that these charge densities, point charge, line charge, surface charge, and volume charge. So these charges can be used to produce the electric field intensity by using the Coulomb's law, yeah, chapter 2. So similarly, for the current chapter, for the current lecture, if we have the current density, we have the I, Js, and J, we can use them to calculate the magnetic field intensity by using a law which is called as Biot Savarts law. Yeah, Biot Savarts law. Yeah, right. Okay, so we can say that based on this, yeah, the reason why I put this slide is that I just want you to understand that the method of using the Biot Savarts law, yeah, is somehow similar to the Coulomb's law that we have learned in chapter 2 before. Yeah, so that's why I've mentioned in class so many times that you need to have a good grip in electrostatic topics, yeah, because that will be very useful when we learn about the electrostatic field later. Yeah, right. So back to this slide, we're going to see the Biot Savarts law. Yeah, we're going to learn about Savarts law, which is the first law that can be used to calculate the magnetic field intensity. Okay, and this Biot Savarts law is comparable to the Coulomb's law, yeah, as I mentioned before. Okay, then let's have a look at the Biot Savarts law. This is based on the experiment done by Mr. Savart, yeah, and Mr. Biot. That's why the law is named after them, yeah, Felix Savart and John Baptiste Biot. Okay, so this is an experiment done by them in which it has this DC current, yeah, DC current, and there are four compasses, yeah, four compasses with a needle, yeah, it shows the needle of the compasses, okay, and the compasses are located at a distance of r from the line current, yeah, all of the compasses are located at the same distance of r from the line current, and this are the observations made by Savart and Biot. In which it says that if we consider that this will be the z direction, okay, and if we use the cylindrical system of coordinate to explain about the behavior of the field direction, we can see that the current is flowing in the z direction, yeah, and the H field is given by or is in the direction of phi. So how can we know that, or how can Biot and Savart know that the H field is in the phi direction? Because when the current is flowing through this wire, it can be said that the compasses, the needle itself, will flow in this phi direction, as shown here in the diagram. Yeah, that's why the observation made by Savart and Biot is that when the current is flowing in the z direction, the H field will be in the phi direction according to the cylindrical system of coordinate. Yeah, and the thing is that the H field will be uh, proportional to the I. Yeah, means that the magnitude of the H field, the strength of the H field will be proportional to the I. Yeah, as we increase the I, the H field will be increased. This is given by the reflection, yeah? The deflection of the needles, yeah, given by, so the strength of the magnetic field intensity is represented by the deflection of the needle, okay, and also it's given that the H field intensity is inversely proportional with the r squared, the distance, yeah, the distance of r. Means that as the compasses is located away, yeah, or further away from the line current, the H field magnitude is said to be reduced. Yeah, it's said to be reduced. Yeah, as we increase the R, H field is said to be reduced. That is why the H field is inversely proportional to the distance squared or R squared. Okay, so these are the observations made by Mr. Biot and Savart, and this is the basis on how they generate the equation of Biot and Savart, in which they produce this equation. Remember observation from Biot Savart just now that H is proportional to the I. Yeah, H is also inversely proportional to the R squared. Okay, and further on it said that I is in the Z direction. Okay, H obtained is in the phi direction. So if based on this, the observation made by Savart, we can see that H is proportional to the I, H is inversely proportional to the R squared, okay, and knowing that I is in the Z direction, okay, so need to have a cross product with the R in the vector, yeah, because we know that dl should be in the Z direction, yeah, yeah, ideal is in the Z direction given by this direction of Z. So Z cross R will give us, yeah, Z cross R will give us the direction of phi. So which is similar to the observation made by Mr. Biot and Savart. Okay, so I believe that you have understand this concept of cross product in our lecture number 1 on the vectors. Yeah, so if you forget about this, please refer back to lecture 1. Yeah, the slide on lecture 1 on how the Z cross R can give us the phi. Yeah. Okay, so that is the equation for the H, which is H is integration of I dl vector cross in the vector of R over 4 pi R squared, or we can have it also as integration of I dl vector cross R, yeah, cross R, direction of R divided by 4 pi R power of 3. Okay, so that should be the methods how we can calculate. Yeah, we can calculate the H field density. Yeah. Okay then. Right. Sorry, I think I made a mistake here. It's not R vector of R. My mistake. Sorry for that. Yeah, make a mistake. Okay, sorry for that. It's my mistake then. It should be a vector of R. Yeah, a vector of R. Okay, I think that should be clear now. A vector of R. Yeah, because a vector of R is given by R in the vector over the magnitude of R. Okay, and that is equal to the vector of R over R magnitude, because we use the magnitude of R to be equals to R capital. Yeah, so that's why we can write that R in the vector. Sorry, it's my mistake also. Sorry for that. In the vector of R to be equals to the vector over the magnitude. Okay, that should be the correct version. Okay, and that's why we can say that from this relationship, yeah, in the vector of R just now has been represented by the vector over the magnitude. That's why we have the R vector over the R power of 3. So from R squared just now we have R power of 3. Yeah. Okay, so that's which should be the substitution of in the vector to a terms of vector itself. Yeah. So R in the vector, let me recall it back. R in the vector is equal to R vector over the R magnitude. So we have these equations here. Yeah. The same things applied for, this is for the case of the filament current. Yeah. So what we have obtained here is for the case of filament current. So the same things applied for the case of surface current, where we have the IDL shall be now substituted by the JS vector ds. Yeah, so we have JS vector ds cross product the vector of R. So we can also have this as JS vector cross R vector, okay, and divided by 4 pi R power of 3 and the ds. Okay. So initially ds is multiplied with the gs vector, but ds can be taken to the right hand side. Yeah, the most right hand side is going to have this, yeah, because we have to integrate it to find the high H field, yeah, to find the H field. Okay, so the same thing is applied for the volume current. Yeah, volume current, we have this form. Yeah, initially you have J vector dV crossing the vector of R over 4 pi R power of 2. So by substituting R unit vector to be R vector over the R magnitude as given here, we can write it as integration of J vector cross R vector over 4 pi R power of 3. Yeah, we have 4 there. Yeah, and that should be a dV integration. Yeah. Okay, so that should be the equation of Biot Savarts law, which can be used to generate the H field intensity here for the case of filament current, surface current, and volume current. Okay, then, so part 2 of this lecture will then discuss on the application, on the examples on how Biot Savarts law can be further applied in calculating the magnetic field intensity. Okay, thank you.